Well, hello and welcome to today's topic. We're going to be talking about discrete and continuous functions and how to tell the difference between the two. And where we're actually going to use this is when we start doing some application problems and or some lab activities. And you need to know whether or not you need to connect the dots or whether you need to leave the line or whether you can connect the dots and make the line solid. And so that's what we're going to be talking about, discrete and continuous functions. So our learning intentions are that the student will be able to determine whether a function is discrete or continuous and to identify then the domain and the range of the functions. So we're going to start off with that you can identify a discrete function from a graph, that you can identify a discrete function from a real life situation, and then that you can find the domain and the range of the function. So let's start with our vocabulary that you need to get in your book. So the vocabulary for discrete function is that it consists of separate or unconnected points that are countable. So things that we can count. So the domain and range will be a list of numbers. The domain again will be your x values and the range will be your y values. So please pause and get this into your notebook. Okay, so here is an example of a discrete set of data. And you see that they are just points, and those points are countable. Okay, points that are countable. So I can sit here and I can go, there's 1, 2, 3, 4, 5 points countable. So this is a discrete graph. Okay, so when we go to then identify the domain and the range, again, remember when we have a set of points, we list all the x values and the y values for the domain, and the range is your y values. Your domain is your x and your range is your y. Now, when I see a set of points like this, you might need to come over first, might be easier, and to actually list what each of the points are. So like this is 1, 2. We'll just go ahead and do this one up here. This would be 6, 3. Go down here, 0, -3, -2, -4, and then 3, -5. So it might be beneficial to list those first, and then it makes it a lot easier then to see the domain, the x values. So those would be 1, 6, 0, -2, -3. Now you do need to get in the habit of doing those in order from least to greatest. So in this case, -2, 0, 1, let's see what would be 3, and 6. So when I first showed you the domain and range earlier, I said, okay, for right now we're just doing listing the x, listing the y's, but now I'm telling you, you need to put them in order, numerical order. Okay, the range then would be over here, your y values. And so again, -5, -4, -3, 2, and 3. And then we put them in the brackets. Okay, so that means it is the set that contains these numbers, the set that contain these numbers. Now, I also asked you earlier about whether or not these were functions, and how do we tell whether or not these are functions? And in this case, this would be a function. Okay, so this is a function because it does pass the vertical line test, or none of the x's repeated themselves. Remember, none of our x's repeated. So that one is a function. So let's do the same thing over here to this one. So we're just going to list the points. So I'm just going to get the ones up here in this quadrant first. So we'll do 3, 1. We'll do 3, 3. And I'm going to do 0, -1. And then 2, 0. And 2, -5. Okay, so when I go to list my domain, okay, it is my x values again in smallest to largest. So in this case, 0. The other things we talked about is we don't repeat a number. So 2 and 3. The range is your y values, again, smallest to largest and don't repeat. So we have a -1, 0, 1, 3, and 5. Okay, so those would be your domain and range. So remember on your domain and range, again, smallest to largest and do not repeat. Now, is it a function? Definitely not, because our 3's repeated and our 2's repeated, so this is not a function. Not a function. We could have done a vertical line test and through here and see we would have hit both of those points, or I could have done a vertical line test through there and hit both points. So either way, it is not a function. Okay, so let's talk about real life problems which would give us a discrete graph. So an example might be if you did tickets and cost. So if you went and you bought one ticket, it would cost just a specific amount. It's not questionable where it is. One ticket, maybe that's $10. Okay, 2 tickets, $20, so forth. Oops, $20, so forth. So that would be something that would be a discrete graph because it is countable. The number of tickets are countable. Okay, we're not going to have a half of a ticket. The other would be months. Okay, in 1 month, how much did you save? In 2 months, how much did you save? So we're talking about at the end of the month, how much? And that again would be a discrete graph. It is something that is countable. So just think of things that are countable. Anything that is countable is considered a discrete graph. So hopefully discrete graphs make sense to you. And we'll go on from there. So let's get an example of where you're going to use or how we're going to do discrete graphs. So we're actually going to be writing our own set of points and even formulas for that. And so here is our table. We've got X and Y. So here's what it says. A token to ride a subway costs $1.25. The function X of S, okay, subway, X times. So I'm riding the subway X times. That's what that means. So what would be our set of points? So if I rode the subway 1 time, 1.25. 2 times, 2.50. 3 times, what would that be? 3.75. 4 times, $5. Okay? And then we could just graph that. So we're going to go to our graph and let's put points on there. So this is the number of tickets that I bought to ride the subway. This would be my cost. Okay? So 0, 1, 2, 3, 4, 5. And then I'm going to go ahead and just go up with here. We'll talk later on as we do graphs. We don't all have to set them up exactly the same way, but this would be mine. And so I would say for 1, it was 1.25. And you could even say 0, 0. Because if I didn't buy any graphs or tickets, I would have I would not have cost me any money. 2, 250. Okay. 3, 375. Up here somewhere. 4 would be $5. Okay, and you see how that made us a discrete graph. Now we could also write us an equation because the cost to ride the subway X times would be $1.25 for every ticket. And again, S of X is your function notation. Usually has something to do with what you're doing here. So this would be S for subway cost, X for the number of times that you ride the subway. Okay, not all of them have to do that. The generic again is just F of X, but anytime you can change it to something that makes sense to your problem, the better. Okay, let's do another one here. It says a family has 3 gallons of milk delivered every Thursday. The function M of X gives a total amount of milk that was delivered after X weeks. So again, X and Y. And one of the things that we could always do is we could put on here, this is weeks instead of X, and then this would be number of gallons. Okay, so as we progress, don't just always use X and Y. Use things that make sense to the problem. So again, no weeks, no month, none was delivered. But after 1 week, on the first Thursday that was delivered, they had 3 gallons of milk delivered, right? 3 gallons is delivered. So after 2 weeks, they had 6 gallons delivered. and after 3 weeks they had 9 gallons delivered, and so forth. And so again, I could go to my table, and this would be the number of weeks delivered, and this would be my gallons received, okay, on that. And this one, I might, and I was talking about that earlier, you could always change this to do whatever. In this case, it would make a lot of sense to go up by 3s. So just pay attention. So I've got 0, 0, I got 1, 3, I have 2, 6, 3, 9, and then you could keep going on that. Again, so your equation in this case, the gallons of milk after X weeks would be 3X, right? Okay, so that's examples of discrete graphs and applications in which you're going to see them and need to graph them.